I'm sure that if you have done a statistics subject before, you'll be reasonably familiar with the normal distribution or normal variables. And this is the classic bell curve shape. So symmetrical around the middle, around the expectation, and it drops away either side of that. Mathematically speaking, it depends on two parameters, a mu and a sigma squared. The sigma squared describes a variance, so it has to be positive, sigma squared is greater than 0, whereas mu can be any real number. And this distribution takes values over the whole real line, so potentially tending towards minus infinity and potentially tending up to infinity. Now you'll sometimes hear it also called a Gaussian distribution, after this man with his stylish hat, Carl Friedrich Gauss. Although the normal distribution's density function is always this bell curve, there are two free parameters, the mu and the sigma squared, so I can shift its mean up or down by increasing or decreasing mu, and I can also increase the variance with a larger sigma squared or decrease the variance. So this would obviously describe data where either the expectation is larger or smaller, bigger or smaller mu, but also where there may be more certainty that my observations will be close to the mean, will be a low variance, whereas ones where I have much more uncertainty as to where it is relative to the mean will correspond to a larger variance, a larger sigma squared. So I've plotted up 6 different normal distribution curves here. Now they're all this classic bell curve. So if we start looking at the solid red shape, the normal with mean 0 and variance 1, if I compare that to the dashed red one, that's got mean 2 and variance 1. So it's the same shape. It's no wider, it's no flatter. It's just moved 2 units up. Whereas if I compare, for example, the solid red curve to the solid black curve, it has the same expectation. They both have expectation 0, based on mu being 0. But the variance of the solid black one is much smaller than of the solid red one. So that means all of the observations will be much more likely to be tightly packed around that mean. So the curve is taller and narrower. Compare that to the solid blue one. And again, it is still the same expectation of 0, but with a larger variance. So it flattens out. So I'm still expecting values on average 0, but we'd be much less surprised to see ones quite a bit larger than that, or quite a bit smaller than that. And you can just pause this if you like and look through the others and convince yourself that the first parameter, the mu, is deciding where the peak of the distribution is, where the middle of the distribution is, and that the sigma squared parameter is deciding how tall and tightly packed or short and spread out it is. I'll focus particularly on the solid red curve here, because that's what we often call a standard normal variable. And that's a term we'll hear again and again. And that just means a normal distribution scaled so that the mean is 0 and the variance is 1. Now the reason that that Gaussian distribution is so common, so ubiquitous, so normal in statistics is what's known as the central limit theorem. And what this says is that if I take samples, x1, x2 up to xn, and these are independent variables drawn from the same distribution, the only assumptions I'm making is that the distribution that these x's are drawn from has finite mean mu and finite variance sigma squared. If I take all of these x's, work out the sample mean of them, and I would do that by adding them all up and dividing by the number that there are, calculating the simple arithmetic mean. If I then subtract away the mean of the distribution they're drawn from, mu, divide by the square root of the variance over n, so the square root of sigma squared over n is sigma over the square root of n, then as my sample size grows larger and larger, the distribution of this difference between the sample mean and the population they're drawn from mean, divided by the population variance over the sample size n, square rooted, will be approximately a standard normal for large samples. And what this means is that whatever distribution, and my only assumptions are that the mean and variance are finite, whatever distribution I draw samples from, then for a large sample, then I can say that the square root of the sample size times the sample mean minus the population mean will tend towards a normal variable. It's asymptotically normal for large samples of size n. We won't formally prove the central limit theorem in this subject or in this video. If you're interested, you can do it with characteristic functions, if you wish to look that up. But we are going to justify visually why it works. Now, I like this simple example of just taking Bernoulli random variables. So in this case, Bernoulli random variable, parameter 0.1, is a variable which 10% of the time it takes the value 1, and 90% of the time it takes the value 0. And if I've got more than one of those, potentially, I can add up n independent Bernoullis with parameter 0.1, and I'll get a binomial with parameters n and 0.1. So for n equals 1, I've just got a Bernoulli. So what I've got here is I have something that 90% of the time it'll be 0, 10% of the time it'll be 1. Now that's clearly far from a normal variable. It's very skewed. It's certainly a very short range. If I make n equal 2, well, 90% of 90% of the time, both of my Bernoullis will be 0, so their sum will be 0. 10% of 10%, i.e. 1% of the time, both of them will be 1, so their sum will be 1 plus 1 equals 2. And the rest of the time, 18%, they'll be 1. So one will be 0 and the other will be 1. So these are both still very, very skewed. They're nothing like a normal shape. And the most likely value is still 0. If I up the sample size to 20, so if I take 20 draws from this Bernoulli, even though each Bernoulli is far more likely to be a 0 than a 1, when I've got 20 draws, and I've only got a 10% chance of a 1 on each, I'd expect about 10% of 20, so about 2 on average. And that's what we can see, that getting 1 or 2, or even 3, is more likely than getting 1. So it's actually pulled the modal values, the most likely values, away from 0. So this is still not a normal distribution. Of course it's not. It's discrete, it's a count, it's still very skewed. If I increase it to 100 draws of this, again we can see that values around 10, i.e. 10% of the 100 draws, are the most likely values, and it's getting much, much more symmetrical. It's getting much more bell curve-like. I mean, it's still discrete, it still doesn't take negative values, so it is not a normal variable. But as my sample size gets bigger and bigger and bigger, if I work out the distribution of the sample mean, I start to see that it looks more and more and more normal. And this is a case for the distribution that I start with, which is anything but normal. That top left one, the check pattern blue, it's very skewed, very short range. But even for this distribution, the distribution of sample means from it will tend ever more towards a bell curve.